That's where this came from. And as a result, we got really motivated to teach people about the oceans. We wanted to do this because we felt education was the most significant part of our experiment, to teach people about what's going on in these incredible bodies of water. So one thing you should know about the water is naturally basic, which means it's got a pH above 7. And the reason it's naturally basic is because the majority of the sea animals, or many of the majority, I'm going to say the majority, are shellfish, made predominantly of calcium carbonate. And the sand you generally see is crushed shells. White sand beaches is mostly shells. Calcium carbonate is a fairly insoluble compound, but in water, over time, it does in fact break apart into the calcium ion and the carbonate ion. The calcium ion is a resident in the waters that the generation after generation these animals use to build their shells. The carbonate, which is an ion, it's a negatively charged ion, is naturally a base. What you have to understand about acids and bases is this. An acid, by definition, will donate a hydrogen ion. A base will take a hydrogen ion from a system. That's the system we're talking about right now. The carbonate ion will take a hydrogen ion, meaning that it's basic. And therefore the water, over millions of years, is around a pH of 8.3. So when we say acidification of the oceans, people think, well, when I put my hand in it, it doesn't feel acidic. I don't burn my skin off. What do you mean acidification of the oceans? Well, the deal is this. The pH has dropped over the last 20 years from 8.3 to right now approximately 8.2. And you would say, well, that doesn't sound too bad. Except that the pH scale is logarithmic. And if you do the calculation using the anti-log of the negative pH, which is a math lesson in itself, what you see is there's been a 30% increase in the concentration of the hydrogen ion that has resulted in this drop in the pH. So the question is, where is that coming from? So here's the ebb and flow of carbon dioxide. Carbon dioxide is a natural resident in the atmosphere. It has to be. If it weren't, we wouldn't be here right now. Carbon dioxide is a greenhouse gas. It keeps the temperature of our planet very constant. Now here's the deal. For 800,000 years, we've done research and found definitively, this is unarguable, that the concentration of CO2 in the atmosphere has been up to, but not exceeding, 300 parts per million, which does not sound like a lot. That's 0.03%. Of this air is carbon dioxide. It's very little. However, that seems to be just enough to keep the temperatures moderate. But what's happened is we stumbled across fossil fuels, and we've been burning them since the Industrial Revolution. We got light, we got heat, we got electricity, we got transportation, we got cooking, we got everything we ever wanted from this incredible discovery that coal, oil, and gas are readily available in great abundance, and all we need to do is burn it. Nobody thought that this was a horrible, horrible experiment that was going to upset the equilibrium in our atmosphere. Now, in the 70s and into the 80s, researchers started to say, in fact, I would probably say going back to the 50s, which the studies first started, but certainly by the 80s, they noticed this increase in the concentration of the CO2. And they decided, as a sort of world body, it should never get above 350. 350 parts per million should be the limit. And today, the concentration of the CO2 in our atmosphere is 408. And when I first started learning about this and started to teach about this was probably around the time of the 2010 Olympics. And I started to read all kinds of stuff. And at that time, the concentration was about 375. And every year, the awareness is raising, and the need to do something about this has gone on, but it just keeps rising. We're now at 408. and it's going up. The 350 was determined to be the tipping point. If we got to 350, things will go out of control in this horrible negative feedback loop. We'll get higher temperatures. Higher temperatures will result in glaciers melting. Glaciers are white and they reflect heat back. Oceans are blue and absorb heat. So it just becomes this perpetuating thing. Carbon dioxide and methane are natural residents of permafrost. Well, the permafrost is melting, and therefore these gases that have been kept in the ground for hundreds of thousands of years are now being released, and it perpetuates the problem even more. And all the while, we keep saying, let's continue to burn more oil, coal, and gas. Okay, now, what about the relationship then between the atmosphere and the ocean? Because we've established that the oceans naturally got this acidity is much higher than you probably imagined, 8.3 down to 8.2, but 7 is neutral. Water is 7 out of your tap. We understand why the water is 8.3, it's because of the calcium carbonate. There's naturally CO2 in the atmosphere, has to be. We wouldn't be here otherwise. Look at Mars. But it's increasing through our input. It is without a doubt, it's unarguable, is anthropogenic, which means that we're doing it. It had never exceeded 300 parts per million in 800,000 years until the last 150 years. If you go further back than 800,000 years, you will find times on this planet when the atmosphere was far higher than 400. But it's never changed at the rate that it's changing. It's never changed over decades, it's always changed over millennia. So it is without a doubt anthropogenic. We are causing it. That is unarguable. Now, the CO2 in the atmosphere has always gone into the oceans. 30% of the atmosphere's CO2 is absorbed by the oceans. This can be a good thing because 1 out of every 10 breaths you take is oxygen that's been manufactured by the ocean. So without the ocean, we wouldn't survive. Okay, our oxygen levels would be too low. So we need the CO2 for photosynthesis. Many of the things in the oceans are photosynthetic. But what's happening now is we've gone beyond what the photosynthetic organisms can keep up with. And so the CO2 is going into the water and is not being used for photosynthesis. And CO2 and H2O form carbonic acid. And carbonic acid is actually a weak acid, but it is the acid that is adding that extra hydrogen ion to the oceans and seeing this drop. Now, there's 2 scenarios coming up. The first scenario is we say, this has gone on too long, and we need to very quickly electrify our transportation, our industry. We need to see cruise ships going by here that are run on batteries. This will be a difficult challenge, but it needs to be done. That would be an abrupt drop in the CO2 production. And with that, they say that the pH will probably continue to go down to about 8.1. And we've heard of this word bleaching. Bleaching is sodium hypochlorite, but it's got nothing to do with bleach. It's just bleach because it looks like the coral's been bleached, it's turned white. Because in the coral, which is actually a living organism, is this little animal called a zooxanthellate. It is photosynthetic and it produces the food for the coral. When the coral is stressed by a low pH and sort of the brother of acidity, which is higher temperatures, you get the coral gets stressed, and its reaction is to expel the zooxanthellates, and they are the ones that provide the color to the coral. So the corals become white in their appearance and are basically starving themselves. You want to say to the corals, don't do that, you need those, but they do this and they become this whitish color. And but they will, in fact, now this is for Paula, because there is hope, Paula, because it's been found in many places around the world that where conservation efforts have been made, the corals come back. And they do become to be prolific once again and regain their color. It's also been shown, like for example, what about these crabs you've seen? Also an exoskeleton, arthropod, they are a calcium carbonate shell. What about them? They're horribly affected by the acidity because in their younger stages, when they're building their shell, they're not finding the calcium that's required because of this acidification process, and so they burn more energy to just build their shell. And their shells are also thinner and weaker, and they become more susceptible to predators. However, they've found, again, in areas where there's been great effort at conservation, that these animals have actually been able to recoup and survive if given the opportunity to come back to their natural state. There's evidence all over the world where this is possible. But the danger is if we say, no, this is not a problem, the oceans are too big, how egocentric we must be to think that we could influence such a massive body of water. And it is without a doubt, we are very capable of influencing this body of water. And we are changing it. For instance, Sylvia Earle, she's got a wonderful show on Netflix, not a show, but a movie, a documentary. Sylvia Earle, her documentary is called Mission Blue. You should all watch it. Sylvia Earle is the most influential researcher in the oceans today. She's probably 80 years old. She is the queen of all knowledge of oceans. And she says, the greatest threat to the oceans today is ignorance. It's not industry, fossil fuels, it's ignorance and not willing to say, yes, we're capable of changing. So people say, I've asked her, should I have children? Is there a future? Is there hope? She says, if your children understand and can help, then yes, have children. Because we need the next generation. And it's my contention that the current student body in high schools today, their awareness raises, and they're the ones that are going to go out and they're going to set up massive marine sanctuaries, and they're going to develop technologies that will electrify cruise ships and airplanes, and it will happen. It took us 10 years to put a man on the moon. 10 years before they landed on the moon, they didn't have a rocket. So if they can do that, they can definitely do this.